Okay, so hello everyone. My name is Scott Grizzard from the University of South Florida, at least for this semester. This is Calculus Spring 2021 Pandemic Remote Calculus. Today is Lecture 2A. We're going to be doing computing limits. This lecture is slightly different than the notes. So last semester, so the last lecture was very theoretical. And last semester, people told me that this lecture, the thing that I had in there for the formal definition of the limit, was too theoretical. So, and that's two very hard theoretical back-to-back lectures, which was kind of stinky. So what I've done is I've moved that lecture, but the notes, so half the notes are now something that's going to be an extra. So not this week, but next Monday, I'm going to do an extra lecture, totally optional, on the formal definition of the limit, which used to be this lecture. Based on feedback from last semester, I've decided to change this lecture to something more along the lines of just how to, not just how to, but techniques for computing these things to help you with the homework and the quiz questions and all that stuff. So this lecture is a little different, so the notes are slightly out of sync. That stuff was in the notes, but I used to not lecture on it, so I'm going to take the part that I used to not lecture on, I'm going to lecture on it. I'm going to take the part that I used to lecture on and make it an extra on next Monday. So I encourage you to watch that, but again, that's an extra. This is going to be much less theoretical than it was last semester, if you watched last semester's. Okay, so let's go ahead and let's talk about what we're doing here. Yep, see, the tablet's syncing now. So what we want to do is we want to talk about how to compute limits, and then we want to talk about this major theorem, two cops and a drunk. Okay, so this is kind of where we, the type notes contain this stuff too, but they also contain a bunch of stuff that's being moved. Okay, so what we want to do is where are we going? Well, we want the formal definition of the derivative and an intuitive notion of what that means. Okay, so this formal definition of the derivative is this idea of a limit being fixed. Okay, so I have this idea of this formal definition of a limit as sort of the limit of the secant lines. And I used to have an animation for that, but I don't know where it is. And then we also have this intuitive definition of a limit the intuitive definition of a derivative as kind of a nudge. So in order to talk about derivatives formally, in order to prove things about derivatives, such as the product rule, the sum rule, and all those things, we need to get at this idea of a limit, and we have to be able to compute this. So the ultimate goal is to be able to compute this. Okay? So that's what we're going to be talking about tonight. We're going to be talking about how do you compute these limit things. Okay? And we're going to have a couple techniques for computing them. So that's sort of the idea. Last time we talked about the limits of sequences and intuitive limits. Okay? Problem set 2, which we're going to do on Wednesday, is going to talk about the limit laws. So what we're going to do there is we're going to get formally into the limit laws. But today we're going to do this is going to be a little bit more, let's dig in and do some examples and kind of get at this idea of how we can compute these things, and also an intuitive notion that's actually a formal notion. There is a formal definition of the limit that's different than the one in the book, because the one that I'm going to give you relies on sequences. But it's actually a much more intuitive definition. It's not as useful if what you want to do is prove the limit laws. And those proofs are on the back of the book in one of the appendices. But this definition is much more useful in terms of how to understand how to get at these things. But you need the definition of a sequence, which is what we did last time. And then we're going to talk about direct substitution properties, which is kind of how you go about computing these things. And then we're going to, and then I'm going to show you kind of the way that you format these problems, and the different types of formatting you can do and what's important. All right. So are there any questions up front? I saw some questions about quiz grading. There were the quizzes, a bunch of them have been graded. Some of them, the retakes aren't all graded yet. Problem set grading is being done, but they're not all there yet. So stuff of the grading thing, I mean, there's a lot of stuff here. There's a lot of stuff to grade, so it is getting done. Are there any other questions? Okay. So yes, so this is the lecture. No, so this is the lecture. This is lecture 2A for Sunday. Remember, there are 3 lectures a week: Sunday, Monday, and Wednesday. Monday is usually either a review or an extra. Except of course during test week, because I put both lectures. And then so this is lecture 2A. This is actually one of the ones you're computing. Okay. So if I understand your question correctly, are there any other questions? And of course, tomorrow is Martin Luther King Day. I thought I might not give a lecture, but I decided to do it today because tomorrow I'm going to do a review. That is, of course, optional, and most people will not attend that because basically what I'm doing is going over fractions and stuff and radicals and stuff like that, and just algebra that you may or may not remember. So in case your algebra is a little weak, I'm currently enrolled in a class, and I've discovered that I've forgotten all of my vector calc. I'm enrolled in a graduate class, and I've discovered I've forgotten all my vector calc, so I spent a good deal of today reviewing that. So even, reviews happen even once you reach the PhD level. Okay, and remember that the smartest people ask the dumbest question. Okay, I'm not sure what you mean by is this on Blackboard. No, this particular, there is no class tomorrow during the day. So the normal thing where we would have a class during the day, it's MLK Day, we don't have class, if that's what you're asking. Okay, so let's jump in here to what we've done here. So last time we talked about limits of sequences, okay? And then in peer leading, you talked about intuitive limits. So you had this idea that, this is from peer leading, you had this idea that I had like a function here, right? F, right? And then I had this point here. And then I had this idea here. This is A. So we'll call this 1, 2, we'll call this 3. And then we'll call this 1 here. So I had this idea, here's F. And I have this intuitive notion that as I get closer and closer to 3 in the X space, I get closer and closer to 1 in the Y space. So I had this idea that the limit as X approached 3 from the left of F of X equaled 1. And I had this idea that the limit as X approached 3 from the right of F of X equaled 1. Therefore, the limit as X goes to 3 of F of X equals 1. Now, contrast that with this idea. Right, where I had this idea, here's 1, here's 2, here's 1, here's 1.5. So contrast that with this idea here, where I had that the limit as X goes to 2 from the left of F of X equals 1, while the limit as X goes to 2 from the right of F of X equals 1.5. Therefore, the limit as X approached 2 of F of X does not exist. Okay, so how do we feel about that 1 to 5? This idea from pure leading where I had to have the limit from the left equaling the limit from the right, right? How do we feel about that? Okay. And then I had some basic functions, like this is a very important function. Okay, this one here is f of x equals 1 over x. And this is probably the most important, this is one of the big, it's not the most important function, but it's one of the big important functions that we have when we talk about these things. Right, so I have this idea, f of x equals 1 over x. So at 1, 1, I have there at negative 1 here. Here, when I'm at 2, I'm at 0.5. Here, when I'm at 0.5, I'm at 2. Same thing here and same thing here. So this right here is f of x equals 1 over x. And I had an example on pure leading. Right? So the limit as x goes to positive infinity of 1 over x equals 0. The limit as x goes to infinity of negative infinity of 1 over x, that should be a negative infinity, of 1 over x equals 0. The limit as x went to 0 from the right of 1 over x equaled, so if I go to the right, I go to positive infinity. The limit as x goes to 0 from the left of 1 over x equals negative infinity. So the limit as x goes to 0 of 1 over x does not exist. Okay, so 1 to 5, how do we feel about the intuitive notion of those infinite limits? Okay. And then, so let's look at another example. Let's look at sine of x as an example here. Okay, so people are a little uncomfortable with this idea. So let's go back and let's talk about it. Okay. So here, as I get closer and closer to 3 as the x space, what happens to y? Right? So as I come from the left, what happens to y here? What does y get closer to? All right. Yeah, it approaches 1. And then as I come from the right, I also approach 1. Okay. If I zoom in on this function, I get closer and closer to 1. And let's look at another one, and let's pull it up on Desmos. Am I zoomed in properly here? Zoom. Reset. All right. So let's look at this last one. People are saying that they understood the first two, but they missed this one. All right, so let's look at this function, 1 over x. All right, now, as I go to infinity, what happens to this? Right, so let's pick some numbers, okay? And this function is very important. It's called the reciprocal function. Right, this one gets closer and closer to 0. And this is an important function. It's called the reciprocal function. Okay? And it's defined as follows. Let x equal negative infinity to 0, union 0 to infinity, y equal to, it's actually the same thing, but we're going to say r. Okay? Now, f, so this one is called recip. There's several ways of denoting this function, but it's actually a very important one. So it kind of gets its own thing, right? So the recip of is defined from x to y so that recip of x equals 1 over x. Okay? So how do we feel about this idea? I've got this function that I'm just calling recip, and its definition is that it's 1 over x. Okay? Kind of weird formal language, but, that's what it is. All right? And it has a graph that looks like you'd expect. So, by the way, if this graph here for 1 over x, if you're not comfortable with it, change that. So if you don't, this graph should be in your function library. Okay, this is one of the ones, this is one of the biggies. I need to start OneNote, don't I? So this is one of those big functions. All right, this is one of those that you should just know. If someone says 1 over x, this graph, this picture of 1 over x should just appear in your head. Okay? It's that important. It's kind of one of the biggies. All right? So, if you need to print this, I would print this on a sheet of paper and put it over your bed. Look at it at night. 1 over x. When you say 1 over x, right? This is f of x equals 1 over x. It's the big one. It's a big one. F of x equals 1 over x. Very important function. Yeah, I should actually say recip because I'm doing it here. Right, this is one of those big functions. It's like sine, cosine. It's one of the really big ones. Okay. And this brings us to this idea, right? So let's take this is the sample point method. Okay. So note that this will not compute the limit at all times. But let's look at what the sample point method does. Okay, so let's look at the sample point method. Okay, so what I'm going to do is I'm going to take 1 over x. I'm not going to write recip all the time. So I'm just going to say let f of x equal recip of x equal 1 over x. Because I don't feel like writing recip. It's too long. I'm just going to write f. Now, okay, now to compute the limit as x goes to infinity of 1 over x, I am going, and I shouldn't say compute, I should say to guess. I am going to take sample points. Okay, in particular, I'm going to take 1, 2, 3, 4, right? So f of 1 equals 1, f of 2 equals 0.5, f of 10 equals 0.1, f of 100 equals 0.01. F of 1,000 equals 0.001. F of 1 million equals, what is that, 10 to the negative 6? Okay, so what number is this approaching as I get smaller and smaller? As my x space, x here, as x gets bigger and bigger, y goes where? Y goes to 0. Okay? Right, so this is the sample point method. These are the x's, and this is the y. 1 to 5, how do we feel about that idea? I take a whole bunch of sample points and I make a guess. Okay. But beware of the sample point method. It can lead you astray. All right? So let's look at f of x equals sine of x. So let's look at the limit as x goes to infinity of sine of x. Not sine of x. Let's do sine pi x. Okay? So what is sine of pi times 1? Okay, well, let's look. So if I go a pi, I get 1. I get 0, correct? Sine of 2 pi equals 0. Sine of 10 pi equals 0. Sine of 100 pi equals 0. Sine of 10,000 pi equals 0. So 1 to 5, how do we feel about that? Right, I plug in a bunch of numbers. Okay. However, remember this is the northiness, right? So if I'm north of, so what's the northiness of 1 pi? It's 0. What's the northiness of 2 pi? Well, I went around the circle all the way once. Now, every time I'm even, n times pi, n is even, I am here. Because I've gone all the way around the circle every 2 times. This right here is n pi if n is odd. Okay? It's a good question. Good question. However, watch what happens when I do this. The sine of pi times 0.5 equals 1. Sine of pi times, okay, right? Because I'm right here. What if I go to 2.5? Well, that would be 1, 2, and a half. That also equals 1. What about sine of pi times 10,000, 0.5? Well, I'm going to go around 500 times and then hit 1. So here, if I did this method, I would wind up, so I think from above, the limit as x goes to infinity of sine pi x equals 0. But here, I would think, no, I don't think, I think, the sine of pi x goes to 1 as x goes to infinity. Okay? So how do we feel about that, 1 to 5? I'm being led astray. Okay? All right, here I've got a sequence going to thing. Yes. So because I have a sequence going to 1 and a sequence going to 0, in fact, the limit does not exist. And that is a very good observation. If I have two sequences going to A, where F, so if I have two sequences, we'll call them S, we'll call them R and S, right? So that R, the limit, so Rn goes to, we'll call this, we'll call it y1 as n goes to infinity. But Sn goes to y2 as n goes to infinity. But so that Rn goes to A, sorry, this should be an x, as n goes to infinity, but f of Rn goes to y1, and f of Sn goes to y2, y1 not equal to y2, then the limit as x goes to A of f of x does not exist. Okay? So here, and so how do we feel about that observation? I wrote that observation. They are approaching different values in very technical terms, right? So here, this example would be, so this would be S, this would be Sn. This would be f of Sn. And this right here would be Rn. And this would be f of Rn. Okay? Right? So what I've done is I've taken this intuitive notion and I've kind of done it like this. Okay? So back to our example. Right? Rn equals, the formula for Rn is pi times times n plus 0.5 Sn equaled pi times n. Okay? So the limit as n went to infinity of Rn equaled infinity, and the limit as n went to infinity of Sn went to infinity. Okay, so how do we feel about the idea that these two sequences, these are both in the X space? Okay, and they both go to infinity. Right? Just this sequence. If I take the limit as n goes to infinity of this sequence here and this sequence here, I get to infinity. Okay? Right? This one here, so R1 equaled pi times 1.5. R1000 equaled pi times 1000.5. R10,000 equaled pi times 10,000.5, right? Whereas S1 equaled pi, S1000 equaled 1000 pi, S10,000 equaled 10,000 pi. Okay? All right. Now, let's look what happens here. So, f of R1 equaled, we've got it up here, 1. That's supposed to be a times, that's a decimal. I don't know why it won't go up. There it goes. Okay, so how do we feel about that? So that's this notion. These f's, so f of Rn, as n goes to infinity, f of Rn goes to 1, while f of Sn goes to 0. Okay? So that's a formal way of kind of saying this idea that I'm going to the wrong spot. Okay? So I have this idea that the limit doesn't exist. Okay? Because I never settle. I have multiple things. As I go to infinity, I have multiple things that this goes to. Right? It could go to 1. It could go to 0. I could pick it so that it went to -1 if I picked odd values here. Actually, 1.5 would go to... I should pick R0 here because 1.5 actually goes to -1. But, oops. Come here. Come here. Erase. Let's pick R0. Because 1.5 would actually go to -1. Okay, so I have this idea that I go off and off and off and to infinity, and it never settles. Okay, so that's why you have to be very careful about this. But this also gives us another definition of the formal definition of the limit. Okay? So what I'm going to say is this. I'm going to define the limit as follows. So definition. let f be a function from some domain. So let D be an interval. And I'm going to put this thing near D. Technically, it's in the closure of D, right? But the idea of this example here, this statement right here, when I say near, right? So, like, example, if D equals 0, 1, then A could be 0.5, A could be 1, etc. Okay, so if, let's say this was an open interval, right? So if this was an open interval, 0, 1, I could have an endpoint. It could be the endpoint, right? So it's defined near the thing. Or it could be in it. Okay? 1 to 5, how do we feel about that? And I actually don't need D to be some interval. I just need it to be some collection of intervals. Some union of intervals. I really don't care. It's got to be something that has intervals. F be a function from D to R. Okay. So here's our definition. The limit as x goes to A, L some real number. The limit as x goes to A of f of x equals L if for every sequence S so that Sn goes to A as A goes to infinity, f of Sn goes to L. As this should not be an A, this should be an N. Sorry about that. Okay, so here's my form. If every sequence, so that Sn goes to N, goes to A, this is in the X space, f of Sn goes to L. Okay, 1 to 5, how do we feel about that? Matter of fact, let's get rid of this weird notation here from the beginning. Let's just get rid of this. We'll just go with the intuition here. Let f be a function whose target is the real numbers, A and L be real numbers. A is in X space. L is in Y space. Okay. There's an even better one. So it's not enough for it to just be one sequence. It's got to be all of them. Okay? I have low commitment to that. Don't I? This, by the way, is not in the book. The book has something called the epsilon delta definition, which is good. I'll write it down here. This is the book's version here. And this is what I'll talk, book definition. Okay. Let A in the X space, L in the Y space, F a function F the limit as x goes to A of f of x equals L if for every epsilon greater than 0 there exists delta greater than 0 so that for all x let's see, how did it do it? So it does for all x so that if it uses this word if x, the absolute value of x minus a is less than delta, then f of x minus L is less than epsilon. So this is called the epsilon delta definition here. This is what I'm going to talk about next Monday. So there is a technical definition that the book has. I prefer this one for our purposes. So let f be a function. And again, this is too much. Let's just let f be in the x space. And let's do something simpler. Again, this is all preamble. Let f be a function with a in its. Let f be a function. Let's do it like this. Let f be a function. Sorry, this is my first time using this definition in this class. I used to use this definition, but it's who cares? It's too complicated and it's not intuitive. Let f be a function with a in the x space or near the x space, L in the y space or near the y space. Now the with a in or near and L in or near. Now it's important to note that this definition will actually handle infinity. The book's definition will not. They'll have separate definitions for every sequence S, so that Sn goes to A, f of Sn goes to L. There we go. That's better. Okay, 1 to 5. How do we feel about this revised definition now that I've made you write it 6 times and confused the hell out of you? Okay. All right, so let's do, but that captures the idea of what we want. Okay, so I've confused a bunch of people. Sorry about that. I've made it worse and worse, but it captures this idea that if there's one that doesn't go, I don't have a limit. Okay, that's the idea, and that's this kind of guesstimation technique. Okay. All right, well, in order to figure these out, let's do an example of the direct substitution technique. So let's do some computation examples. Okay, so let's do this for an example. The limit as x goes to 6 of x plus 5. So what I'm going to do is I'm going to stick in 6. Okay? So let's just stick in 6. This is called direct substitution. And what I'm going to do is I'm going to stick in 6. So I'm going to do 6 plus 5. That equals 11. Okay? 1 to 5. How do we feel about that? This trick, this is called DS. Works on the following types of functions: polynomials, rational functions where A is in the domain, radical functions where A is in the domain, and trig functions where A is in the domain and algebraic combinations Okay, so all I did was I threw in the number and I wrote direct substitution. Now I have to make sure I have a polynomial or something like that. Another example: the limit as x goes to 0 of x plus x squared plus 1 over x minus 1. Okay? Now, so I plug in 0, and I get 0 squared plus 1 over 0 minus 1. Okay, well, that's just 1 over negative 1, which equals negative 1. Okay? How do we feel about that? 1 to 5. Right? I've got a rational function here, but 0 is the bottom note does not equal 0. So I just throw it in, and I've got this is an example. So this is a polynomial. This one's rational. Okay. Now, trick 2. So if I get something like 0 over 0, my next trick is going to be factor it. So let's do an example. The limit as x goes to, let's go to 2, of x squared minus 4 over x minus 2. Now, I try to plug in 2, and I get 0, right? I get 4 minus 4 equals 0, and I get 2 minus 2 equals 0. 0 over 0 is something we called indeterminate. It's bad. We can't do that. So, I need more work. Okay, so what I'm going to do is I'm going to factor this. I'm going to factor the top. The top is a difference of squares. So I'm just going to do a little algebra on it. I'm going to do the limit as x goes to 2 of x minus 2, x plus 2 over x minus 2. And you might want to check it. Now, the x minus 2's cancel. And I'm going to wind up with the limit as x goes to 2 of x plus 2, which equals, now I'm going to directly substitute, because now when I do this, I'm going to wind up with 4. So now I just directly substitute, I get 2 plus 2, which equals 4. Okay, so 1 to 5, how do we feel about that one? Okay. Now, another trick we can do is multiply by the complex conjugate. Okay. So, example. Let's do the following. The limit as x goes to let's see, I want the square root. Let me do that later. Let's do the square root of 2 minus, let's do x minus the square root of 2. And let's do x squared minus 2 on top. And this will be the limit as x goes to the square root of 2. Or we could do the limit, yeah, let's just leave it like that. Okay, or let's make this x minus 2 on top. I'm sorry, I'm going to do this to you. Let's make this a square root of x minus the square root of 2. And let's make this 2. There we go. That looks nicer. Okay, so what I'm going to do, if I sub in here, notice that directly subbing in here, I'm going to wind up with root 2 minus root 2 equals 0. And I'm going to wind up with 2 minus 2 equals 0. So I'm going to have to do some more work. So what I'm going to do here is, okay, I've got the limit as x goes to 2. Now there's two ways to do this. I could factor the top as a difference of squares, right? I could do that. That's clever. Or I could just multiply by the conjugate. So what I'm going to do is I'm going to do x minus 2 over the square root of x minus the square root of 2 times the square root of x plus the square root of 2 over the square root of x plus the square root of 2. 1 to 5, how do we feel about that idea? I can multiply by by the conjugate. Not a complex conjugate, just a conjugate. Okay. Now, if I do that, now, here's the trick. The part that you're not having the conjugate apart, okay? So the part that doesn't have the square root, leave this alone. Do not multiply it. Okay? That's the trick. Big tip. You need to leave this alone. Okay? So what happens when I multiply this out? I'm going to leave the top alone. Right? This could have been on the bottom. If the leave the thing that does not have the square roots alone. I'm just going to leave it like this. bottom here I'm going to multiply out. So this right here is going to be x minus 2. The middle term disappears, and I wind up with x minus 2. Okay? Leave this term alone, because it's the term that's going to cancel. Okay? Now I'm going to sub in. I'm going to get square root of 2 plus square root of 2. I'm going to wind up with the square root of 2 plus the square root of 2 equals 2 root 2. 1 to 5. How do we feel about that? And note that the important bit here was to leave that thing alone. Okay? All right. Okay. Well, let's talk about limits of infinity. But in order to talk about limits of infinity, I'm going to have tricks to deal with limits at infinity. By the way, these tricks work for limits at infinity too, but there's special ones that work for limits at infinity. Okay? So, okay, these only work they do not work for a's that are finite numbers. Okay? So, theorem. Okay. Let P and Q be polynomials. Okay. P equal Cn x to the n plus Cn minus 1 x to the n minus 1 plus dot 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 plus C1 x to the first plus C0. Q equals Cm x to the m plus Cn minus 1 x to the m minus 1 plus dot 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 plus these should not be C's, these should be A, something other than that, so we'll call it A. am minus 1 a1 x to the first plus a0. Okay, these are rules, so they should really have the x there. So 1 to 5, how do we feel about this idea of two polynomials? How do we feel about this idea of polynomials? Just checking. Broadcast is working. Yes. Okay. All right. So I'll define what a polynomial is in a minute. Then the limit as x goes to infinity of p of x over q of x equals the limit as x goes to infinity of Cn x to the n over am x to the m. Okay, this is called nothing else matters. Okay, example. And the same thing holds for negative infinity too. And the limit as x goes to negative infinity of p to the x over q to the x equals nothing else matters. The limit as x goes to negative infinity of cn x to the n over am x to the m. So let's give the example. Do the limit as x goes to infinity of, I don't know, 10x cubed plus 5x squared plus 3 over negative x to the fourth. Well, I'll do that last. So let's do 200 minus x to the fourth. Okay? So 1 to 5, how do we feel about that setup? Now, what I'm going to do is I'm going to apply nothing else matters. Okay, because these are two polynomials, one on top of the other. And I'm going to get the following. Okay, well, nothing else matters. Lim as x goes to infinity of the biggest term on top is 10, is this x to the cube term. So 10x to the cube. And then the biggest one on the bottom is that negative x to the fourth. So these things are going to cancel. So this whole x cubed is going to cancel. That's going to become a 1. And I wind up with the limit as x goes to infinity of 10 over negative x. And that is going to equal negative infinity, right? Because that's negative x over, that's negative 1 over x or negative 10 over x. You actually don't care what the coefficient is at that point because you go to negative infinity. For another example, let's do the limit as x goes to infinity of x squared plus 10 over 5x squared would equal nothing else matters. The limit as x goes to infinity of, okay, so I just want the top term. So this would be x squared over 5x squared equals the limit. And then those x squareds will cancel. And I wind up with the limit as x goes to infinity of 1 over 5. And that just equals 1 over 5. 1 to 5, how do we feel about that last one? But again, these are tricks that only work for these only work for limits to infinity. Right? So this only works when that's infinity, or negative infinity. It would work for negative infinity too. Okay. So people were having questions about what a polynomial was, so let's do some definitions. Definition. Okay. Let P be a function. P is a polynomial if for all x in the x space, or the domain, P of x equals a n x to the n plus a n minus 1 x to the n minus 1 plus plus a 2x squared plus a 1x to the first plus a 0x to the 0. Okay, that's what a polynomial is. Example. f of x equals x squared is a polynomial. G of x equals x to the fifth plus 2x plus 1 is a polynomial. H of x equals 1 is a polynomial. How do we feel about that? That's the formal definition of a polynomial. It's some function that only has positive exponents of x, and it's just addition of those terms. There's some way to do it, right? Alpha of x equals x plus 1, x minus 1 is a polynomial. Since alpha of x equals, if I multiply this out, I get x squared minus 1. Okay, questions? Okay, so people are saying that they have problems with the definitions. Okay, that's understandable. These definitions are hard. And the idea of doing a definition is difficult. So let me give a little justification for this, okay? We don't actually care if 10 years from now you can spat out the definitions of some of these things, right? And 10 years from now, I don't care if you remember the epsilon definition of the limit of a sequence, okay? I do, however, care about the technique of learning them, because formal definitions are going to be around for your whole life. So there's a trick on how to learn them. And let me give you an example about that, okay? So here's an example of that. And I'm just going to state it for you. We're going to do this next time. We're going to play with this next time. Okay? But I care about the way that you memorize. This is a theorem. It's called Two Cops and a Drunk. It is one of the more important theorems that we're going to have playing around. Okay? All right. So here's how it goes. Let f be a function a in or near the x space, L in or near the y space. Okay? Here's the preamble. Now here's the theorem. If, okay? For all x near a, okay, and top and bot so let f, let's do this. Let f top and bot be functions I didn't do this well. I need 3 functions. Let f top and bot be functions a near or in the x space, L in or near the y space. If for all x near a, bot of x is less than or equal to f of x is less than or equal to top of x, and the limit as x goes to a from the left of bot of x equals the limit as x goes to a the left of top of x equals L, then the limit as x goes to a from the left of f of x equals L. Okay, so here's the theorem. Two cops and a drunk. Now, you're talking about not being able to memorize a theorem or get the intuition behind a theorem. Okay, here's the key. What I want to do is I want to make a picture. All right, that's the trick. Okay, so let's look at what this thing actually says. Have a function f. And f is just kind of hanging around. Let me put f a little higher. All right. I have a point called x. I'm sorry, a point called A. And here's a point called L. Now, I have two functions, one of them called top, and one of them called bot, which does something like this. I need to make them like this. And this is f. And here's what I memorize. I memorize this picture. I have a top, I have a bot, and I have an f stuck in the middle. Now, for all x near a, top is on top, bot is on the bottom, and f is trapped between. Okay? And then everyone's going to the same place. Right, so top and bot are both going to the same place. That means f is going to the same place. And this is called two cops and a drunk. Because if I have a drunk function in between, but these two cops are stuck in between my drunk function, and they always are going to the paddy wagon, that means that my f has to be dragged to the paddy wagon. 1 to 5, how do we feel about that? And the point is, I don't memorize the theorem. I memorize the picture, and then I write the theorem from the picture. Okay? How do we feel about that idea? So, let's see. Do I have one of these left? So what I'm going to do is I'm just going to work off the picture. Let me see if I've got this picture hooked up. I should have queued this picture up, and I didn't. Let's see. Course image. Nope. Oops. I'm sorry, the internet's driving me nuts today. Do we have any questions, by the way, while I'm looking this up? I'm trying to get this picture for you. Files. Course image. Download. Right, so here's the picture. Let me see, can I zoom? This will not let me zoom, so you're going to have a small picture. So here's the picture. Here's two cops and a drunk. Let's see if it'll go again. There it is. So I got a pick function on top, a function on the bottom, and then after some point, f is trapped in between top and bot. So everyone's going to that same L. 1 to 5. How do we feel about it now that we've seen kind of this picture? And again, that's the thing I memorize. And then I use the picture to construct it. Okay. All right, so what we've done today is we've gone over a couple ways to compute derivatives. We talked about kind of this idea that we have this sort of, we went over the reciprocal function, and when we went over this idea that I could define the limit as if every sequence went to the same spot. And then I had a bunch of computational tricks. And then what I did was I introduced two cops and a drunk. The next time what we're going to talk about is using two cops to compute stuff, using two cops, improving and writing proofs. Okay, are there any other questions? Okay, so again, I'm sorry if the lecture was a little bit shaky. This one's new because I didn't do this one last year. I did a formal epsilon definition lecture. That formal epsilon definition lecture is going to become the subject of next Monday's extra lecture, if you're interested in it. And tomorrow what we're going to do is going to review just like algebra 1, algebra 2 stuff from high school on how to deal with fractions and inequalities, just so you remember them. And on Wednesday, we're going to do writing proofs in the limits of two cops. There's no class on Monday, which is tomorrow. There's a lecture in the evening that's a review, but there's no class on Wednesday. What we're going to do is we're going to play with a problem set on computing limits. And the quiz for Wednesday, I wasn't sure if I'd get to it, but I will. I wasn't sure how far I'd get tonight, so the quiz for Wednesday will be posted. It's just not yet. Any questions? Okay, well, that's it for me. Have a good evening, and I will see you all in class on Wednesday, if I don't see you tomorrow. Let's see. Stop streaming.